Hello, everyone. We'll maybe give it a minute or two as people trickle in from the headliner presenter, including myself, as also moderating that session. Let me just see, do we have our first speaker here? I think our first speaker should be Diana or Lily or one of the other authors on this paper. Looks like maybe not yet. Well, we have 6 presenters, so maybe just in the interest of time, it looks like Nuria Coma-Cros is here.
Yes, that's me.
Great. So maybe we can start with Nuria, if you want to share your screen.
Yes.
And then just briefly for everyone, so with 6 presenters, possibly 5, you'll have about 20 minutes total, including sort of any time for questions. But we'll also take questions in the chat box. So if we're running low on time behind schedule, I might just ask that you answer questions in the chat box. So
Okay, sure.
go
Can you
ahead.
see my screen?
Yep.
Okay, yeah. So my name is Nuria Coma-Cros, and I'm a PhD student at Erasmus University Rotterdam. And today I'm going to present my research on factors and mechanisms influencing the adoption of sustainable fuels in the Dutch inland shipping sector, which I'm doing together, of course, with my supervisors. So for those who are not so familiar with this transport mode, we speak about inland shipping when we talk about goods or people that are moved in inland vessels through rivers, canals, or lakes. And this is a very important transport mode in the Netherlands because it transports 1/3 of transported goods. Today I'm going to talk a little bit about the problem we are trying to address, the theoretical approach we used, the research question and the methodology, and also some preliminary findings of our study and the next steps. So the problem we are trying to address is that 95% of vessels still use fossil fuels. However, the inland shipping sector has agreed to become zero emissions by 2050. And there are several innovations being developed, such as alternative fuels, but also new sources of energy, such as solar energy, and also propulsion methods. But we know actually that many transport innovations are never implemented as they have to fight an existing system that is based on fossil fuels. And it's actually really complex because the transport sector is also related to many other elements within society and policy. So we want to explore more this part, and we want to know exactly what needs to happen for these innovations to be adopted in the Dutch inland shipping sector. Our theoretical approach is based on transition and innovation theory. We understand transitions as a process of change from one system state in equilibrium to another. So in this case, we want to move from a system based on fossil fuel to a system based on zero emission fuels. And we are interested in understanding what factors influence the adoption of innovations in the Dutch inland shipping sector. For our research, we've been mostly inspired by Faitelson and Solomon framework on the adoption of transport innovations. And here you can see how they map different factors which they connect to 3 types of feasibilities, technical, social, and political. And well, we think that most attention is often given to technical feasibility. So we want to have perhaps a wider approach to the adoption of innovations. And we also want to answer to calls to study more the dynamics behind the innovation processes. So how exactly are these factors related and how exactly do they influence each other? So our research question is, what are the factors and mechanisms influencing the adoption of more sustainable fuels in the Dutch inland shipping sector? And by factors, we mean the different elements of the sector. And by mechanisms, we mean the ways in which these factors are related to each other. And sometimes these mechanisms create some feedback loops, as they are more known in the in academia. So it can be a positive feedback loop that ultimately leads to a system-wide change, or a negative feedback loop that stabilizes the system and leads to this lock-in situation. We developed a methodology based on 6 steps for finding factors and mechanisms. The first step was the selection of innovations. The second step, the data collection for the selected innovations that then we coded. And then as a fourth step, we did a code co-occurrence and thematic analysis of this text. Which we then translated into causal loop diagrams, which we are now validating with expert interviews. And now I'm going to explain all of these steps. So for step 1, we selected the innovations. And well, first of all, we came up with a list of the most mentioned innovations after reading 100 news articles from the Nieuwsblad Transport. This is a respectable journal in the inland shipping sector. And this was the list of the most mentioned innovations. But we selected hydrogen, LNG, which stands for liquefied natural gas, and biofuels, because these are 3 innovations that are all fuels that can work in different vessels, regardless of the type of cargo they transport. But more specifically, we focus on hydrogen because it has obviously received a lot of media attention, but also economic investments. However, it is an early stage innovation, which means that the factors that are influencing its adoption are still evolving, and which also means that there's little information about this innovation. So to balance this potential lack of data, then we decided to include LNG. LNG is a high maturity level innovation, and then we expected quite a lot of data on it. However, we understand that it is not a zero emission fuel, as it is still a natural gas. And so we understand that its future is quite uncertain in this zero emission road. And then we also chose biofuels, which is an innovation that had very high expectation in the early 2000s. It was even included in the EU directives. However, now it's losing visibility, and perhaps it has been sort of stuck in this early stage of innovations as well. So we wanted to understand what happened with this innovation. After having this selection done, we collected data and we collected news articles, but also scientific articles. So we started with 336 news articles and 157 scientific articles. And after removing duplicates and other texts because of, for example, focusing on other locations such as China, we ended up with 180 news articles, with quite a lot of them focusing only on LNG, and with 33 scientific articles. So we coded this text with Atlas TI, and we ended up with 9 code groups and 69 codes. But for this study, only 7 code groups and 32 codes were relevant. So in this picture, you can see the round boxes are the code groups and the square boxes are the codes. And well, these were related to the innovations we were studied. studying, but also infrastructure factors, for example, in relation to supply, bunkering, also instruments, for example, in relation to laws or subsidies, also market economy factors, such as demand or industry interest, organization factors that relate to the way in which actors cooperate, for example, the rationale behind an innovation, so what reason is put forward for the adoption of this innovation, and especially the need to reduce emissions. And the last group of factors was related to the traits of the innovation itself, so maybe more the technical aspects of it or the resource availability related to that innovation. So then we wanted to find out which ones of these codes were most frequently mentioned for each of the three studied innovations. So we did this code co-occurrence analysis of the different factors with the studied innovations. So this is here what you can see, and on the left you can see the coefficient, so the code co-occurrence coefficient. 0 means that these two codes never co-occur, and 1 means that these two codes co-occur every time they are used. So yeah, there's quite a lot of information here, and now I will delve more into each of these three innovations we studied. So for biofuels, we found that what was particularly important was the resource availability factor. And this is related to the fact that, well, biofuels are limited, especially if other industries like aviation want to make use of them. So then, because of this reason, other alternatives were put forward, and biofuels are seen as a temporary solution. And also the technical aspects of biofuels was relevant because it is said that biofuels can damage vessel engines. And because of these reasons, actually, the instrument of loss was frequently mentioned because then the mandatory blending obligation of biofuels that was initially discussed in the EU was actually never implemented here. The story of LNG starts with, well, the importance of supply, bunkering, and storage infrastructure, and also vessels. And, well, I think this is just a reflection of the fact that LNG is a more mature innovation, so there's more infrastructure and more vessels that currently use LNG. And then also the technical aspects of it was really relevant, especially in relation to safety. And that is why the instrument of regulations was also important, because it was said that safety regulations needed to be in place for the adoption of LNG. And then last, for hydrogen, we can see again here supply and vessels were relevant factors. Not so much because they are already existing, but more because hydrogen is a very different type of fuel than fossil fuels. So it is assumed that we would need very different types of infrastructure and engines to be able to use it. To understand more how can we use hydrogen, there is a lot of research being done at the moment. So that's why here this instrument was frequently mentioned. And then another interesting factor was the fact that many alternatives were talked about, and this is because it is understood that, well, hydrogen is not yet available to be used in the market. So we will need other alternatives in the meantime. And then to understand better the relationship between these factors and what exactly, how exactly they are connected to each other, we look at the quotations that connected each of these codes, so the factors with the innovation. And then we did a thematic analysis of these quotations. So for example, this is a quotation that was coded with both the code biofuel and resource availability. And it starts by saying there are different types of biofuels, some of which are a lot more environmentally friendly than others. What is particularly important is the source. So with this type of quotations, we came up with this theme that says biofuels can reduce emissions, but their sustainability is questioned due to their source. And later it also says this puts great pressure on the food industry. Large areas of land were taken to grow raw materials. So here another theme called biofuels compete with food and land was created. Then from these themes, we were able to create these causal loop diagrams. And this is the example of biofuels. And here you can see there's different boxes. So these boxes are the factors that were initially used as well in the coding of Atlas TI. So the same color scheme has been kept. And then each of these colors then has, it relates to different type of factor. So for example, red are market economy factors. And then these factors are connected to each other with these lines. And each line has either a positive sign or a negative sign. So a positive sign means an increase in one factor leads to an increase in another factor. So for example, if we have more appropriate vessels and infrastructure, then this would need more financial resources. And then a negative sign means that an increase in one factor leads to a decrease in another factor. So the more financial resources that are needed to modify this infrastructure and ships, the less interest the industry would have in adopting this fuel. Basically, this diagram it's quite complex, and I don't have time to go too much into the details of it. But it's really useful to see, how the factors are connected to each other, and what factors and what type of actions can we use if we want to influence the adoption of this fuel. So this can be very relevant for policymakers in the field to see what buttons can be pushed. And then maybe as a summary and preliminary results of our research, we can say that the causal loop diagrams capture the complexity behind the adoption of innovations in the Dutch inland shipping sector. And by looking at the mechanisms and feedback loops that exist between all these factors, we can explore the dynamics between these different types of factors. And this is still work that we are doing at the moment, so I cannot say much about it yet. And then more specific results for each fuel. So what we find in biofuels is that there are questions about their environmental performance and also consequences for engines. Also the influence of resource availability on scaling up. So because we don't know how much biofuels will be available in the future, this might have an influence on the amount of scaling up that we can do of this fuel. And then this is a reason for adopting other types of fuels. And this causes uncertainty about the future of biofuels in general. And we found that here two policy instruments were particularly important, which is laws and agreements. For hydrogen, what was particularly important was the collaboration between actors, and this was especially in relation to research and development projects. So this type of instrument, together with regulation and subsidies, appear very frequently. And we think subsidies have a very important role to play in hydrogen because its technical characteristics make it so different compared to fossil fuels that large investments will be needed for the adoption of hydrogen. So subsidies can play an important role. And then for LNG, we found out that initially it was a positive business case because LNG was cheaper than diesel, although that changed. So now it's not a positive business case anymore. However, it was useful because it changed the mindset of the industry and it helped them to see that there is another alternative to diesel. So at least that happened. But of course, we now also see that it's an off-the-road alternative because it's not a zero-emission fuel. What we can also learn from LNG is that several instruments were put into play. So all the ones I've talked about here, so laws and agreements, regulations, all those also appear for LNG, also together with the need to spread information and train crews and communicate was also very relevant. And then we can also see that the maturity of innovation is relevant for the type of factors that were identified. So as you can see here, these different innovations have a different type of instruments that, that were relevant. And we can also, of course, also see that for more mature innovations such as LNG, we did have much more information available. And last, we can conclude that the methodology we created in 6 steps was an effective approach to go from textual data, so from scientific and news articles, to creating these causal loop diagrams that we are now validating with expert interviews. So as the next step, as I said, we are conducting these interviews, and here you can see some of the stakeholders we are talking to. And well, of course, we hope to write and publish the paper, perhaps this upcoming months. Well, thank you very much for your attention. And if you have any questions or want to know more, please just send me an email. Here is my email address. Thank you.
Great, thanks, Nuria. I think just given that we have our first speaker in the room now, and in the interest of time, maybe we can do questions by the chat box. Sorry, I think Diana, maybe you had some challenges that I know maybe some have had challenges that we had to change the Zoom link. But if we can maybe switch to your presentation now.
Hi, Jason. Can you hear me?
Yes.
Yes, I've had some connection challenges. Actually, my student Angelo, he's on the call, so he's the one who's presenting. Yeah.
Great. Okay, Angelo, do you want to share your screen now?
Hello. Let me see. Yeah.
Great.
Can you see my screen?
Yep.
Okay.
But it looks like I think you need to share the other version of your screen.
Okay, let me see.
It should be under, I think if you go under slideshow, if I have it right, it should give you, yeah, perfect.
Just only this one. Okay.
No, it looks right now.
And now?
Sorry, it was correct.
Please go back to the previous approach.
Yeah.
But why?
So I think you just need to, you can share your screen and then.
Sorry, just let me 1 minute, please.
Okay.
Angelo, is there any way you could go back to that approach that you had before? Have we lost him?
It looks like he's still here.
We may need to move on
Yeah,
then.
if you want, you can pass the next presenter, please, and then I
Okay,
can.
sure. So Hanya, maybe
Sorry.
can you? Our next presenter is Maryam Khatami. I see she's in the room, but she also shared a presentation. Would you like to present live, Maryam?
Hello, can you hear me?
Yeah.
Yes.
Yes, I'm ready to present.
Great.
Perfect,
So
go
if you
ahead.
can share your screen and
Okay.
yeah, and then just if you can make it full screen.
Well,
Perfect.
hello everybody. Thank you for your presence. My name is Maryam Khatami. I study in Department of Railway Engineering and in Iran University of Science and Technology. Our article title is Efficiency Optimization in a Gasoline Truck Routine, a case study. The different parts that we have in our research is introduction, literature review, methodology, case study, conclusion, and future directions. First to introduction. Well, the important issues in transportation of dangerous goods are risk analysis, location, and routing. And the aim that we research in our article is pathways with 5 realistic criteria to find the optimum route from the origin point to the destination point of gas station. And this aim is important to us for 2 aspects. The first aspect is because of the economic activity to invest in it, and the second aspect is safety criteria to minimize the risk. And the tools that we use in our research to assess the risk are FTA and ETA charts, FAST and Aloha, GAMS, and ArcGIS. In the following, I will tell you the acronym of this software. The literature review, first I tell you the articles that help us in our research. We want to search about the reasons of accident of hazardous material transportation. And the article from Japari et al. They invest on 657 accidents, and they understand that the most cause of these accidents are because of human factors, with 60%, in the following vehicles, environmental, packaging, and loading hazardous material. And the highest number of the accidents are because of LPG, and then gasoline and diesel. And another survey is a survey on accident in the road transportation of hazardous materials in Brazil. NATO has a survey on 4,638 accidents, and they understand the average of 140 accidents per year. And the result from this article are the accident is between the time of 10 a.m. to 11 a.m. And most of these accident happens in urbanization and the industrial vocation, and the other result is the tipping over is is another cause, and flammable liquid are another cause, and soil with the most impacted element has 86% of accident, and value of 36 accident victim happens per year, unfortunately. We also have read some articles that use ArcGIS software as we do, and the first and important one that we use it in our article too to expand it is from parts of et al. That they define scenarios based on safety and economic indicators using 5 important criteria with multiple criteria, and to find the optimum route with ArcGIS software. And the other article is from Zhang, that they assess the risk for a dangerous transportation of dangerous goods to minimize the cost and optimize the safety by combining GIS and genetic algorithm together. In our methodology, we use some methods. First of all is about a what-if method. The case study of our article is fire of a fuel tanker carrying 20,000 liters of gasoline. And what-if method is a method that decision maker use it to understand the consequences of their decision, and they identify the obstacles and then use them to make the better decision. What we do in what-if method, we prepare some question about the happens and the cause of the event, and we search about what is the consequences of that event, and what should we do, and what recommendation or suggestion can we say to prevent that problem. I will tell you some of this question for just a little example. What if they carry more than the capacity of the gas tank? It causes leakage and fire. So it is recommended to fill about 90% of tank. And what if they stop and park of a tank for a long time on the way? It cause explode and a spark. So it is recommended to drivers to don't stop a long time. And what if the tanker is unlabeled? So when fire happened, the fire extinguishing will be affected. So before the moving, the labels must be added. The other method is FTA, fault tree analysis. In FTA, we have minimal cut set and basic events and top events. It's from up to down. And here in this method, we have the main event, and we search for the causes of and reasons that why this event happened, to prevent from that event. For example, the top event is a fire of a fuel tank, and the event of it is a source of fire and leakage of the gasoline. For example, for source of the fire, the cause are a spark and a spontaneous combustion. And the spark has some basic events that cause a spark, such as cigarettes, mechanical failure, electronic connection, illegal action, and lightning. the last method is ETA, event tree analysis. This method has initial event and the consequences of it. It's happened when the system didn't work properly, and after the event, the consequences happen. And in a simple way, it means that the event happened, and after that, what should we do? For example, the initiating event here is fire. The first step A is providing sufficient foam to suppress the fire. It works or it didn't work. If it didn't work, it goes to next step B, using put fire extinguishers, and it goes on like this: C, using of halogenated hydrocarbons; D, using sand; E, forces of emergency and rescuing; and F, immediate action of prevention of population from there. And after all of these stages, if they didn't happen, the consequences happen ED. ED means environmental degradation, that is destroying environment, and in the last and the most dangerous stage, it causes injury or death. Okay, we come to our case study. Our case study is oil put in northwest of Tehran. It's called Shahran, and it is one of the 3 depots in Tehran. Its products are gasoline, gas oil, and kerosene, and it has 11 tanks and a storage capacity of 220 million liters, and it supplies 60% of gasoline and consumes 20 million liters per day. We have a mathematical model for our problem, and in our model we define 5 criteria, and for each of these criteria we define 5 risk factor. And in this issue we I want to select the shortest time that we for each route from the oil depot to each of the gas station. We have 3 routes, and we choose that shortest time by ArcGIS, and with the model we find the top route. For first criteria, first factor risk is population risk, and it has buffer 800 meters, and we have this formula with the number of people on that route on the maximum people of our routes. The other one is travel time. Travel time is from the formula of length of that trip and the average speed of each route. The other risk is risk from distance of distance from a fire station. We have buffers here too. The range of buffers is from 0 to 800 meters, and the risk factor for it is 0. And it goes on like this to the to more than 4,000 meters with a risk factor of 1. And the risk factor of distance from centers of higher sensitivity, when there is no sensitive building, we give risk factor of 0, and otherwise the value is 0.1. And the last risk factor for environmental location is in that buffer range. if this environmental location was there, the risk is 1, and otherwise is 0. So we talked about criteria, what we search for to minimum the population on the path, the shortest possible route, proximity to relief centers, keep away from centers of higher sensitivity, and keep away from environmental location. And each of these criteria were weighed according to the parts of our article, and we put it in a functional object, and we have 3 concentrate. The first one, it means that all the vehicles should use only one pass. And the second one means that the capacity of that vehicles, they should carry less than the demand. And the last one is some of the time and the service and the visiting must be more than the quickest time for visiting that pass. We also use Aloha software in our research to simulate in more detail, to understand that how these materials can affect the environment and how dangerous the energy radiation could be for that environment. The inputs that we use here is weather, area, and temperature. And it determined us 3 areas of 30, 70, and 99% tar rate. And the radiated energy is with 3 regions. The red one is the most dangerous with 10, the orange 5, and the yellow with 2. And then we use ArcGIS, and we particularly put 34 of gas station here, and the layers here are population, pavement, and control layer, and gas station, and then put the 5 criteria and optimal route created by network analyze tool, and the best path for 34 gas station was chosen. And also by using the modeling GAMS software, we choose the best routes for each of the tankers. And I bring randomly 4 of these gas stations here in more detail. And at last, we use fast software to, in addition to check and see how the materials spread. For example,
Maryam, just in the interests of time, maybe do you have a conclusion slide that you could go to?
Yes. As at last, as a review and conclusion, we identify the optimum routes by considering the different safety and economic criteria to find this optimum route, and using ArcGIS model and mathematical model of GAMS, and we use geographic distance to decrease in cost and to increase the safety of our model. We use the criteria population risk indicators, short distance from relief centers, and the distance from valuable and environmental places. And we simulate this accident in Aloha and FAST to get other items such as the hazard radius and amount of material radiation and the temperature. And at last, we have some future direction. We recommended to have some of these factors such as human factors analysis, like driver behavior and training them, and integration of real-time data for unexpected conditions such as traffic and weather, and use of newfound technology, IoT, and machine learning algorithm, and broader geographic area. We using different cities with different traffic patterns and environmental impact study, use of fuels and vehicles technology to reduce the carbon footprint. The references are here. Thank you for your time and attention.
Great. Thank you. Thank you very much, Maryam. I think, again, just in the interest of time with these 6 presenter sessions, we really are very tight on time. There's a bit of a discussion in the chat, though, so if you want to take a look at that. It sounds like Angelo is ready to present now.
Yes.
Yeah, so if you want to share your screen.
Okay. So there we go again.
Perfect.
Okay, hello. Sorry for my previous issue. My name is Angelo, and I'm presenting research on diesel truck emissions from freight trip generation impacts on air quality of port cities, with a specific focus on Oakland, California, which is our case of study. Basically, this research explores how freight activities contribute to air pollution in urban areas, particularly affecting vulnerable neighborhoods. So freight-related air pollution is a major concern in industrial areas, particularly in cities with large freight hubs like ports. Businesses in these areas emit CO2, CO, NOx, hydrocarbons, PM2.5, and PM10, which are harmful to human health. And unfortunately, the transportation sector lags behind others in reducing its environmental impact. In this slide, I want to emphasize the significant impact of freight-related air pollution in urban areas, particularly in cities with heavy freight traffic. It highlights how air pollution disproportionately affects vulnerable neighborhoods near industrial and commercial areas with concentrated freight activities. The map on the left visually represents the priority neighborhoods in Oakland, California. It shows that these neighborhoods suffer the highest fraction of annual deaths attributed to air pollution, underscoring the critical need for targeted interventions in these communities. So our research focused on 3 main questions. What is the impact of daily freight traffic on priority neighborhoods in Oakland? What environmental impacts, particularly air pollution, are produced by these freight activities? And lastly, is there a correlation between air pollution and health-related impacts in these neighborhoods? In our literature review, we compare our approach with other studies, and we found that we focus on detailed data integration by using confidential business establishment data and truck counts from the Port of Oakland. Our study is more granular, analyzing data at the business level within specific industry sectors and ZIP codes, which allow us to provide actionable insights for local policymakers. This is our methodology. So we use freight trip generation models tailored to Oakland's businesses, along with stratified sampling and shortest path network modeling to estimate travel distances and calculate air pollution. So our emission factors were sourced from the EMFAC web database to ensure accuracy for the vehicle types in the study area. This slide outlines the freight trip generation, or FTG, models used in our study, including those developed under the National Cooperative Highway Research Program and the National Cooperative Freight Research Program. These models are based on survey data from New York City and the Capital Region, providing a strong foundation for our analysis. The graph demonstrates the relationship between establishment employment, measured in full-time equivalents, and the daily number of freight orders or shipments generated. Various FTG models are represented in the graph, providing accurate estimates of freight trip generation rates. These models are crucial for analyzing the impact of freight activities on air quality, and by applying them to our case in Auckland, we ensure that our findings are based on reliable methodologies. This slide breaks down the sectors we studied based on the North American Industry Classification System, or NAICS. We focused on the freight-intensive sectors, including agriculture, construction, manufacturing, wholesale trade, retail trade, and transportation and warehousing. These sectors are important to their significant freight traffic, which directly impacts urban air quality. In Oakland, California, for example, over 50% of freight-intensive sector establishments are in the retail trade and food and accommodation sectors, with many located in the port of Auckland. Retail trade and accommodation and food services dominate employment, revealing their significance in both business numbers and job opportunities. This concentration has important implications for freight trip generation and air pollution in the region due to the high volume of goods and services needing transportation to support these industries. In this slide, I want to show you the freight trip generation estimates and truck counts for different sectors within the freight-intensive sectors. The transportation and warehousing sector, along with retail trade, generate over 20,000 daily freight trip combined. Transportation and warehousing represents 12% of the total FTG, and retail trade accounts for 23%. In addition, the Port of Auckland contributes 36% of all freight trips in the FIS, highlighting the significant impact of these sectors on local air quality due to their concentrated activities and heavy daily emissions. So here we can see the distribution of daily freight trips in Auckland, focusing on areas near the port and the airport. The maps show that most trips are concentrated in these regions. The areas closest to the port and industrial zones have the highest concentration of freight traffic. The map overlays trip densities with industrial and commercial zones, highlighting that the CIP codes between the port and the airport are especially affected by high levels in freight activity, with significant implications for air quality and the well-being of local communities. Here, the estimated pollutants emitted by freight vehicles. Most are gasoline-powered, and the average emissions per trip is shown in the table. The maps illustrate PM 2.5 and NOx emissions across Auckland, highlighting areas with high concentrations and emphasizing the environmental impact of freight traffic on local air quality. In our analysis of air pollution emissions, we found that CO2 is the predominant pollutant, contributing 99% of the total emissions. Other significant pollutants include NOx and particulate matter. These findings highlight the substantial impact of freight activities on air quality, particularly CO2 emissions, which are the main source of air pollution in the study area. So this slide provides a detailed look at the distribution of particulate matter 2.5 emissions across different industry sectors in Auckland, categorized by the NAICS. Each map represents the impact of a specific sector on PM 2.5 emissions, showing how these emissions are distributed across various CIP codes. The PM 2.5 emissions are concentrated in the southern and eastern parts of Auckland in the construction sector. Manufacturing and wholesale trade also show significant emissions, primarily in the central and southern CIP codes. Retail trade and transportation and warehousing contribute heavily to emissions in the same regions. And the accommodation and food services sectors shows emissions concentrated in specific zones. So overall, the maps illustrate that the southern and central areas of Auckland, particularly those near industrial zones, are most affected by particulate matter emissions across these key sectors. We analyze mortality rates in areas heavily impacted by pollution to understand the health implications. Our findings indicate that neighborhoods with high levels of PM2.5 exposure also experience higher all-cause mortality rates, especially among Pacific Islanders and African Americans. The bivariate maps show the correlation between high PM2.5 levels and mortality rates. So we can see the darkest areas, which are the most affected regions near the port and industrial zones. So now some policy recommendations. So based on our findings, we propose several policy recommendations. Land use policies should include conditional use permits and zoning overlays to limit the impact of freight activities near residential areas. For the freight industry, transitioning to cleaner fuels and adopting more sustainable logistic practices at ports are essential. Additionally, demand management strategies should be implemented to reduce the presence of heavy freight vehicles in priority neighborhoods, ultimately improving air quality and public health. Our study shows that freight vehicle emissions significantly impact air quality in Oakland, California. So our conclusions basically are addressing or are focusing in the using of the daily local data. We estimate pollution levels and propose actionable policies. So health data indicates that long-term exposure to freight-related pollution has serious implications for vulnerable neighborhoods, and targeted interventions are crucial for improving air quality and protecting public health. Looking ahead, our future work will involve incorporating different scenarios to evaluate additional policies beyond land use changes. We plan to explore the adoption of cleaner fueled vehicles, implement freight demand management strategies, and restrict freight traffic in priority neighborhoods. We will also expand our modeling efforts to include non-freight intensive sectors and service-related vehicle trips, using state-of-the-art models to estimate hourly pollutant concentrations. Finally, I would like to acknowledge the sources and references that support our study. If you are interested in further details, please refer to the bibliography provided. Thank you for your attention, and we are happy to answer any question that you may have, or please reach it to the email of Professor Diana Ramirez. Thank you.
Great. Thanks, Angelo. And also, thank you for getting us back on time. We maybe could take a minute to answer one question live, if there's a question. I posted several in the chat box, but looks like maybe, Cara, do you have a question? Oh, okay. You're just putting your video on.
Well, I do actually. Angelo, why don't you share your camera, man? Can you share your camera?
Oh, I'm sorry. I just
Yeah.
only, I forgot. Sorry.
Oh, that's fine.
And all of you who have not figured out how to add a photo to my profile, this is bothering me because I want to see you. It really means a lot to me, and I think to other people too. Although many of you are on LinkedIn, so I can go try to find your photo. But yeah, there's a lot of Maryam Khatamis. And Maryam, I think you were presenting from Iran. So bravo, you have great bandwidth. Bravo on doing that. And we're all, praying and hoping that Israel and Iran back off one another right away. And
Yes.
It's been very scary to watch. So
yeah. So yes, so Angelo, I put a bunch of questions in the chat box. We can maybe continue that discussion there.
Okay. Thank you.
And we might have a little bit of time at the end because I know one of our presenters provided a video. But let me move on to the next in-person presenter, Laura, who is at the University of Victoria in my favorite city, as some might know, my hometown. So whenever you're ready, Laura.
Okay.
Hey, Laura, where are you right now?
I'm currently at University of Victoria.
Fantastic.
Yeah, nice to hear
Recognize that
Jason is from
downtown.
Victoria as well.
Yeah.
Can you all see my screen?
Perfect.
Okay. And I hope you can all hear me as well.
Yep.
Okay. Hi, everyone. Thank you for joining our session. My name is Laura Deveer. I'm a master's student at the University of Victoria under the supervision of Dr. Laura Mine from the Clean Air Lab at the Department of Civil Engineering at the University of Victoria. I'm excited to delve into the topic for today, which is real-time air quality prediction using traffic videos and machine learning. So on-road transportation is a significant source of air pollution in cities. And in Canada alone, we have over 26 million passenger vehicles, and emissions from these vehicles accounts for a considerable proportion of the total transportation emissions. So what then is traffic-related air pollution? When vehicles such as trucks or buses burn fossil fuels, they release these pollutants into the air, which lead to poor air quality. We are not only considering vehicle exhaust, but then other sources of traffic-related air pollution include tire and brake wear, as well as evaporation of fuels. Examples of these pollutants include volatile organic compounds, black carbon, particulate matter, nitrogen oxides, sulfur dioxide. And a considerable proportion of these form what we call criteria air contaminants. As I mentioned, they lead to poor air quality and their exposure to the human leads to adverse health effects such as asthma, impaired lung function. Considering that 4 out of 10 Canadians live within 250 meters of high traffic roadways, it's very important that we have an understanding of the exposure of traffic-related air pollutant concentrations around us, which leads to why this matters. Why are we trying to investigate traffic-related air pollution? So first of all, this information is vital for active commuters. And by active commuters, we mean the cyclists and pedestrians who are exposed to on-road air pollution during their daily commutes. Having access to this information can help them make timely decisions about their routes in order to minimize their level of exposure. In addition, we are not only focusing on having access to this information, but how accurate and timely this information has been found to trigger avoidance behavior. Also, having access to this information can help us propose solutions to minimize their effects. For example, these days or in recent times, we've seen the implementation of emission control technologies, as well as adoption of cleaner fuels, shifting to more public and active transportation. And a prime example is BC leading the charge for zero emission vehicles. We can now delve into the heart of the matter with our problem setting. So for the problem setting, I've divided it into two main portions where we have exposure assessments or techniques used to measure the exposure of air pollutant concentrations. So the technologies that are used are normally sometimes measurements techniques or modeling techniques. So traditional approaches to investigating variations in air pollutant concentrations employ repeated measurements from regulatory monitoring stations, satellite remote sensors, and traffic detectors. The challenges with these technologies is that they have limited spatial coverage. For example, regulatory monitoring stations are in Victoria, for example, we have one regulatory monitoring station which is responsible for giving us an idea of the air quality in Victoria. And so if we want to measure site-specific data, it's very hard to rely on those measurements for accurate predictions. They also require specialized personnel, regular calibration and maintenance. And due to the low resolution that they come with, they are unable to tell us, or they are unable to give us the accurate or predict real-time variations in air quality, I would say. As I mentioned, they are also resource intensive. They are very expensive to come by. The other stage is modeling techniques, where we have models such as linear regression models, land use regression models. However, these models use simple statistical nature to investigate the linear relationship between pollutants and their predictors. And so it's very hard for them to capture the nonlinear relationship between these air pollutants concentrations and their predictors. As a result, our research objectives are to utilize a cost-effective approach. We don't want to use regulatory monitoring stations, which are, as I mentioned, expensive. And so we want to make efficient use of resources that are already available. I did not mention it earlier, but then since we are also looking at traffic-related air pollution, we need traffic data, which is very hard to come by or is very expensive to come by. And so in that effect, we are using traffic cameras, which are already deployed in our cities for management and surveillance purposes. We also want to demonstrate the ability of traffic information extracted from only videos to accurately predict variations in air quality. And then we want to investigate the relationships between traffic variables and pollutant concentrations. Our study area is Gorge Road, where the city has plans of implementing a bidirectional protected cycle track. And so our main purpose of choosing this area was to have an idea of the air quality before the implementation of this cycle track, so that we can see the level of exposure cyclists might be exposed to, in addition to our main goals that we have. Our modeling framework, I've divided it into 3 main stages, where we have the measurement of the air pollutant concentrations. As I mentioned, we are going towards the low-cost approach. So we are using low-cost sensors to obtain minute by minute concentrations of particulate matter, ozone, and nitrogen dioxide. These low-cost sensors are also able to give us an idea of the meteorological data. And then the issue with low-cost sensors is, as I mentioned, they are low-cost, so they will have their own challenges. And one challenge is that they have, at a point in time, their measurements are inaccurate. So we have to find a way to accurately to make sure that the measurements from these low-cost sensors are as accurate as possible. And to do that, we use machine learning models to correct the measurements. I'll explain in details in the later slides. But then essentially, we train these machine learning models to be able to correct the measurements from the low-cost sensors. And then we essentially use them in our prediction model. The next stage is the extraction of traffic information. And to do this, as I mentioned, we use traffic cameras. So we use videos from these traffic cameras to develop a custom data set representative of vehicles in Canada or Victoria. And then we annotate them. We make use of the object detection model called the YOLO V8 model. And then we obtain traffic counts from these models, and then also extract second-by-second vehicle speeds, which we later use to extract emission estimates using the motor vehicle emission simulator model or MOVES. Our main goal is to have a bigger air pollutants prediction model that has air pollutants measurements, traffic information as predictors, and then emission estimates to be able to predict the air pollutants concentrations. I would move on to the calibration of the low-cost sensor, which is the CTA air quality monitor. So as I mentioned, these monitors at a point in time give us inaccurate measurements. And the reason they do that is they use a light scattering technology. So what they do is they emit light into the air, and then based on how the lights are scattered, they are able to use that to estimate which pollutants are present. The only issue is the air is made up of different particles. Temperature, relative humidity would affect how these lights are scattered. And so there comes a time in its operation where we see gradual changes, which lead to measurement inaccuracies. And so for a couple of months, we deployed a low-cost sensor with the regulation monitoring station we have in Victoria. So ideally, if all things were being equal, they were supposed to give us the same measurements. But as I mentioned, low-cost sensors give us inaccurate measurements. And so the oranges I show are the measurements, the actual measurements from the low-cost sensors. And in an ideal world, they were supposed to look at the greens. They were supposed to look like the blues, which are the measurements from the regulatory monitoring stations. So what I've shown here is a correction that was applied with the random forest model. As you can see, we've been able to correct the oranges to the greens, which are more consistent with the regulatory monitoring station measurements. And so when we deploy these local sensors to our actual study area, the measurements we obtain from those, we are able to pass them through our machine learning model to correct them before we use them for our predictions. The next stage is to extract traffic information. And a very simple understanding of what object detection models do is like they are smart detectives. So they go through different frames of images. We feed it with different vehicle classes in different rotations or in different forms. And so for our study, we used over 10,000 images of different vehicle classes, including passenger cars, passenger trucks, buses. And so when we train it and then we feed it with new videos, it is able to detect what vehicles are present. We're able to also measure the performance of our vehicle detection model after training it, and we obtained a high accuracy of 0.97. Here, I wanted to briefly demonstrate what we have with the traffic information extraction. So as you can see from the video, when vehicles come into the frames of the video, they are assigned bounding boxes with different colors, which tell us which vehicles are present. And then, so after detecting the vehicles, the next stage was to have our traffic counts. And so to do this, we drew a virtual line and then we track the vehicles as they move through the frames of the video. So when vehicles cross these virtual lines, their counts are updated in each direction of the line. And this is how we were able to achieve retrieve the traffic counts. Just a simple illustration of what happens when vehicles cross the virtual line that we created. I just wanted to show some of the classes of the vehicles that we were capturing with our vehicle detection model, as well as just a few counts that we obtained. So we wanted to validate our traffic counts to make sure our models are accurately giving us the correct counts. We first conducted manual counts, and then the City of Victoria also installed a counting system at our study location. We compared it, and then we were able to achieve high accuracies with our traffic counts. The next stage is to extract the traffic speeds. And what we use here is perspective transformation to correct to kind of transform the coordinates that we receive on the road in terms of camera measurements into the real world measurements. And so having knowledge of the fixed this length and then the width of the road, we're able to draw a polygon and then retrieve the coordinates and then transform them using the perspective transformation. We essentially calculated the speed as distance divided by time. Time was obtained from the frames per second. So every video has a frame per second. For example, 30 frames every second. We track the vehicles as they move through the frames, and we are able to retrieve the speeds of the vehicles. A brief illustration of what happens when we include the speed detection or the speed model into our videos. We also validated our speed model. The city of Victoria had a speed radar at our study location, and so we were able to see the kind of measurements we're getting from our speed or our speed model, and then we were able to achieve an average error of 4.02%. I just want to conclude. I only presented the preliminary stages of the research, and so the contribution from these stages, we were able to calibrate our air quality or our low-cost sensor model to make sure that our measurements were accurate. We were also able to extract traffic variables such as count, speeds, vehicle classes, and obtain good performance of the vehicle detection model of 97%. Ongoing work are to integrate the speed estimation with our vehicle emission simulator to obtain the emission estimates, and then use the XGBoost model to predict our traffic-related air pollution. Thank you.
Great, thanks, Laura. Excuse me. Are there any questions? Well, I could maybe ask one question that I know Victoria has a relatively high bike share compared to most other North American cities. Do you think that you know, in some ways affects air quality kind of?
Yeah, definitely. I can answer that because I've currently we've already I didn't mention it here because I didn't want to make it long, but then we've already done our prediction models, and from what we can see, traffic is not really a high predictor for us because Victoria itself doesn't have that many vehicles running through it, and especially Gorge Road doesn't have that many vehicles running through it. So most of our most of the features or predictors that are contributing to the high pollutants levels are normally what we see: temperature and relative humidity, and then background concentrations. And so with our model, we believe that if it was deployed in like a city with higher traffic volumes, that's when we see high influences of traffic with the air pollutant concentrations. But then for now, as you mentioned, Victoria is not ideally a very high traffic centric area.
Yeah. Well, I think the traffic is pretty bad in Victoria.
Well, not as bad as
considering
other places in Canada.
Yeah. Any other questions? We have a few minutes. Maybe I'm kind of partially a question relating back to the previous presentation. Is what do you are there air quality concerns around freight in Victoria? Or I don't even know what the fleet mix is now on the buses. I think that they've switched away from diesel for the most part, but
yeah, with freight, I've actually not looked at that, but then normally it's passenger trucks which are mostly predominant, but then yeah, not too much on freight, I would say, from what I've seen.
Yeah, and I guess this is very specific, but you probably get a lot of emissions along the highway coming in from the ferry where a lot of goods come into the city, but that's mostly agricultural land. So
yes,
yeah,
it will probably disperse away.
yeah. Well, it's good to talk about my home. We should go on to the next presentation. So our last last in-person presentation will be Chenyu Zhang.
Yeah, I'm here. I'm here.
Great. So if you want to share your screen when you're ready.
Sure, sure. All right. Can you see my screen?
Yes.
Perfect. Okay, let's get started. Good afternoon, everyone. My name is Chenyu Zhang. I'm currently a PhD candidate from Department of Civil Engineering at Stony Brook University. And I'm very glad to be here today to present our work, AECIF Night, an attention-enhanced co-interactive fusion network for automatic structure condition assessment in visual inspection. So firstly, let's jump into the introduction part. So the United States has about 620,000 heavy bridges in its inventory, and over 1/3 of them are rated as needing replacing in the bridge condition inspection that is conducted every 2 years. However, manual visual inspection is still the main form of assessing the condition of civil infrastructure in the States. During the inspection, it needs heavy lifting equipment, dangerous head access, and road closure. These limitations of the traditional approach motivate research into automating the bridge inspection using emerging technologies. So we hope that we can aid and eventually replace manual visual inspection using these technologies. Unmanned aerial vehicles is a very cost-effective tool for gathering inspection video or image data. They will reduce the on-site inspections time, labor, and equipment costs. However, UAV can collect thousands of hours of video and hundreds or even thousands of images in every inspection. So that will be too much work for inspectors to manually analyze this inspection data. Well, deep convolutional neural network is an automatic and efficient method to analyze the inspection data. So we can use them to perform the semantic segmentation task, which classifies every pixel in an image. So that is to say, we need to assign a class label to every pixel in an image. So in this way, we can use it to segment bridge inspection images to aid inspectors analyzing them. According to the ASHTO's Bridge Element Inspection Manual, an overall condition rating of a bridge is based on a comprehensive assessment of the bridge elements. And element conditions come from structure elements and their defects. So therefore, it is essential to extract both of the bridge elements and their defects from the collected image data. Based on this, we would like to propose the automatic visual inspection pipeline. To begin with, the UAVs are deployed to carry out the bridge inspection, producing the inspection videos or images, and the gathered inspection images undergo detailed analysis through the DCNNs, providing precise results for element and defect segmentation. So lastly, the segmentation results are interpreted according to the element condition state definition here, based on the defect level, ultimately providing the element condition assessment results. However, to accomplish this framework, there are still several key challenges remain to be addressed. So first of all, currently, most models for bridge element parsing and defect segmentation are separate models. That is to say, they are single task models that can only conduct one task in each model. That will bring some limitations like redundant computation, inefficient use of data, or these models may overlook the potential connection between two tasks that may improve our model's performance when making prediction. Several attempts have explored solutions to these issues, mainly using naive multitask learning models, which directly make predictions from the overall feature embedding learned through the shared encoder. However, the special correlation or special association between elements and defects has not been explored yet. as shown in this figure, the corrosion area has white borderline, and the steel elements have colored masks. If we can narrow down the search area when making predictions for potential corrosion from the whole image to the steel element area only, that will obviously reduce the false predictions for corrosion, like corrosion on the background or substructure. Similarly, we can also reduce the false positive prediction for element segmentation if we expand the search area from the corrosion part. So our objectives in this study, we want to develop a multitask learning for automatic structure condition assessment. And in such a model, we want to design a shared split interaction pipeline. And we also aim to model the feature learning and special attention-based feature fusion in such a model, which I'm gonna talk about in detail in the next section. Okay, in this section, I'm gonna illustrate the specific design for AECIF net in detail. So overall, it has a shared split interaction architecture, and there are some key components in our network. So firstly, we use the shared encoder to extract the shared feature from the input image. Following by the shared encoder, we design two task-specific feature learning subnets to further refine or further fine-tune the shared feature for respective tasks. And this relearning subnets aim to improve the performance for respective tasks. Based on the relearning subnets, and we can get the task-specific features, and we can utilize the attention module to extract the special attention map from the task-specific features. For example, in elements branch, we can extract the special attention map for the element task specific features here. Following by this, we propose a module called interactive fusion module. For example, let's take the defect branch as an example. So we can see here, we use the multiplication between the defect special attention map and the element feature. So by combining them together, so in this way, we can narrow down the search area for defect prediction from the whole image to the potential element area only. Following by the core interactive fusion module, we designed two segmentation decoders to make the final prediction for respective tasks. And to validate our method, we set up some experiment details. Firstly, we developed this data set. It's called Steel Bridge Condition Inspection Visual Dataset. It has 440 high-resolution images, all from real bridge inspection in the States. And these images are collected from the steel plate girder bridges. So they're mainly the primary elements are all steel. So we provide 6 classes of elements annotations for these images, such as bearing, bracing, bank, floor beam, girder, and substructure. We also provide the surface corrosion annotation, which is binary, corrosion and non-corrosion class. For dataset split, we have 304 images for training the model and 36 images for validating it. And we also remained 100 images untouched from the training and validation process to finally testing our model's performance and reporting our final results. So to give more details about our dataset, we have 2 figures to show the data distribution within our dataset. So the left one, it shows the number of element classes presented in per image. So we can see here most images contain 3 to 5 element classes. And this figure shows the number of elements in an image, and this number spans from 1 to 20 plus in each image. So to calculate the performance of our model, so we propose 3 levels evaluation metrics. So the first level is class level. We utilize IOU precision and record to focus on the performance in specific class within each task. Also, for each task, we also have mean IOU, mean accuracy, and pixel accuracy to evaluate the model's overall accuracy in each task separately. And overall, for the whole model, we also have a metric to calculate the overall performance across all tasks and categories. So next part is about experiments and our results. So firstly, we did application study to evaluate the effectiveness of our key components designed for AECIF-net. So if we don't include any specific design, like call interactive fusion module and task specific feature relearning subnets in the model, we will only get the naive multitask learning model. So we, by comparing the naive multitask learning model's performance with single task model, so we found that the naive multitask learning model favors the defect segmentation task, but lower the performance on the element segmentation task. So we tested the performance of our designed two modules, and by combining them together, we get our final AECIF-net. And we can see from this table that it achieves the best performance among all models here, and it can effectively address the limitation of the naive multitask learning model. So following by this, we also compare our models, our AECIF-net, with other 4 state-of-the-art models. So in this table, we can find that our AECIF-net achieves the best among all SOTA methods. So specifically, the MAD-net is a very famous benchmark in this area. Our model achieve around 70% and 8.5% higher IOU on each task, respectively. Besides the task level, we also provide the class level performance evaluation results. This table shows the IOU values for each class. As we can see here, our network achieves the performance across all classes. Besides the quantitative results, we also provide qualitative results. So here we have 5 examples to show our predictions, and we also compare our AECIF-net models results with other 4 SOTA methods. Here, the first row shows the results for element prediction, and the second row shows the defect prediction for each example, respectively. So we can see the AECIF-net generates superior predictions. Specifically for element segmentation, it excels in small and irregular elements. It also provides more precise edge and boundaries for the element segmentation. For the defect segmentation, we can see it provides fewer false positive predictions. Here we have more examples. The second and third row shows the ground truth and prediction for element segmentation, respectively, and fourth and fifth row shows the ground truth and prediction for defect, respectively. And so from this example, so we can see our our model's prediction provide high quality predictions, and these predictions close align with the ground truth. However, deep learning model's complexity is the cost for the performance improvement. So we also calculate the trainable parameter number within this Soto methods to compare them with our AECIF net. We also calculate the model level metric about the performance increment against the single task models. So here we can see our AECIF net model utilized only about 60% of the single task model's parameters, and it achieves the best balance between the trainable parameters and the performance improvement. Finally, we have a case study here. So here we have 10 case studies to show the potential application of our network for structure condition assessment by overlapping the element and defect segmentation results together. And based on this element condition state definition, we can calculate the defect area proportion for each element respectively. And based on the definition, we can get the condition for each element. And it shows that our model is capable of accurately determining the condition of each element for both well-maintained and heavily damaged elements. And in the potential, in future studies, we plan to further expand our data set. And if we have any chance, we plan to apply our model in real bridge inspection. Thank you. You can also find our paper and our code and dataset here. I'm ready for any questions if you have any. Yeah. Thank you.
Great. There's one question, I think, from Angelo that I can maybe read out. And while I do that, if Hanya, if you can get the next presentation ready, which will be a video. So Angelo's question is, given that attention models are often resource intensive and drones typically have constrained processing power, memory, energy resources, how are you addressing these limitations in your deployment? Are you using model optimization techniques, specialized hardware, or offloading computation to external servers?
Wow, this is this is a very good question about
bit of a long question, but you can see it in the chat too.
All right, okay.
So I think the question is, how are you addressing kind of the energy requirements of drones, and also the computation? I assume that computation is happening.
Yeah. Actually, we didn't use any optimization for the spatial attention calculation in our model right now, but this is a very good aspect. Actually, maybe we can consider this in our further studies in the future. Yeah.
Great. And then I think Professor Kaufman had a question about that you can maybe answer in the chat.
All right.
If you or anyone else in the room has some suggestions. They're doing some work on computer vision algorithm training for moving vehicle speed violations and license plate recognition. If you're interested in the topic, or you have some colleagues who might have expertise that would help them out on that.
Looks like Hanya is ready to go. Hanya, are you able to play that?
Yeah, so Hanya, if you can share your screen with the audio. Our last presentation will be Jing Wang from the University of Nebraska.
Hello, good morning, everyone. This is Jing Wang. Today I want to present the topic is enhancing marine container terminal efficiency and environmental stewardship via a novel truck scheduling method using waiting lot. These are the content. Many researchers focus on improving the efficiency of marine container terminal. However, trucks' long-term time can impact the efficiency in three aspects: terminal operators, truck drivers, and the environment. In detail, it weakens the operators' competition with lower level of services and increase the customers' dissatisfaction. Moreover, it will waste the driver's time and money. In addition, due to the falling waiting time at the terminal gate, the truck's emissions noise will pollute the environment. Then, truck's appointment is applied to the marine container terminal. It will mitigate gate congestion, reduce truck turn time. However, it blocks the process of walk-in trucks. Moreover, a crucial element related to TS that has not been considered in any previous study is that it doesn't specify the order in which trucks are served within each time window, which means that trucks will arrive and wait for service at one of the gates randomly. This practice offsets the overall benefits of TS and is a gap in the literature review, which this study aims to address. So this study is to utilize the concept of a waiting area and a TS to improve the scheduling of trucks once they arrive at the terminal. There are several assumptions in this paper. The first one is the container terminals have one waiting area. The second, the waiting area is equipped with the communication technologies that will notify the terminal operator the arrival of a truck and will allow the operator to inform the truck when to proceed from the waiting area to specific line at the gate. Lastly, the implementation of TS at the terminal and that the truck has made a reservation. Information about the truck's transaction regarding where the container needs to be dropped off or picked up in the yard is known. Since there is no previous study that is directly related to this study, the following review focuses on those studies that have sought to reduce truck turn time, considering both the gate and the yard operations. The type of studies is the queuing-based studies, simulation studies, statistical-based studies, and optimization-based studies. Then the aim of the studies is to reduce truck turn time. The gap between these papers and these papers and the current paper is the order of trucks being served and the accuracy of the optimal solutions. The contribution of this paper is to optimize the scheduling of truck within each time window of TS by using a new scheduling scheme that seeks to minimize truck turn time, considering both gate and yard operations, and develop an exact solution algorithm based on general bundled cut-based method. As shown in this figure, shows the process modeled in this study. External trucks arrives at the terminal will first needs to drop at the waiting area and wait there until the called by the terminal operators via a dynamic message sign or the cell phone. Once notified, the truck will proceed to the specific line and at the in-gate. There, the truck will wait for service and then proceed to the designed yard block and B. At the yard, the truck will need to wait for the yard crane to perform at the terminal, picked up and drop transactions. Once the truck received services from the yard crane, it will proceed to the out gate. The time from the start to end represents truck turn time. The proposed optimization model assumes the following operational characteristics. Before we introduce the mathematical model, first we need to put forward some assumptions. The first is only external trucks are considered in this model. The second is the locations of import truck containers in the yard are known, as well as the locations of where export containers need to be stored in the yard. And the loading and unloading time is dependent only on the height of the container. Then each truck will perform a single move per trip. The waiting area has sufficient capacity to accommodate the expected number of trucks that will arrive at the terminal during any 1 hour time window. This is indices. AB is the truck ID, K is position, J is gate line, D is the yard crane. A is the set of trucks, L is the position in the list, J is the set of gate line, C is the set of yard crane. AR is arrival time of truck A at the parking lot. M is large number. SJ is service time at gate for truck A, and SYA is service time at yard crane. This is the size, and this is decision variables. The objective function is to minimize the truck turn time. The first constraint we need to consider is the first and last dummy trucks have only one predecessor and successor at the gate. Then a truck cannot be proceeded before it arrives at the gate. Then the maximum waiting time for a truck before it receives services at the gate. All trucks must be scheduled at the gate. Then if a truck is assigned to a gate, it can only have one predecessor and one successor. Proper time of service for different trucks served within the same lane, based on their order in the queue. A truck can't be proceeded before it arrives at the designated yard block. The order of trucks in the list that is based on the service start time in the yard. Then the truck should be in the position in the list, and there is only one truck per position in the list. The first and last trucks have only one predecessor and successor served by the yard crane. All trucks must be scheduled in the yard block. Then the predecessor relation of trucks assigned to the same yard crane. The relation between a truck turn time and the service start time in the yard constraint is the domain of the decision variables. Then the solution methodology, we use the general bundles decomposition based algorithm. And in the constraints, the master problem is 1 to 7. It only one set of unknown variables. Then the slave problem, the sub-problem, test if the solution of the master problem satisfies the remaining constraints by finding values for the other set of decision variables. This is the experiment aimed to demonstrate the benefits and applicability of the proposed model and the solution methodology. We have 10 experiments, and the independent variables is number of trucks, number of gate lengths, and the number of yard cranes. This is the one small case for experiment 1. This is the input data for experiment 1. There are 4 trucks in experiment 1. The arrival time is for each truck is 0, 23, and 28, and 62 minutes. This is the PJ. PJ is the service time at the gate. JY is the travel time from gate to yard. PY is the service time in the yard. Traveling. YY is traveling time between each truck pair. For example, 120 means for the containers of truck 1 to the locations of truck 2. The containers is 100 seconds. The yard current need to travel 120 seconds from the locations of container for trucks 1 to the locations of containers for truck 2. This is experiment 1 results. You can check if you can check that for the TS truck system without proposed scheduling scheme. The truck to the service start time is 23. It means that there is no. It means it based on the first arrive first service policy. However, in our proposed system, the third trucks will get the service first. And this is the waiting time at the gate. For the total waiting time at the gate for the traditional TS system is 32 seconds, but for our system with the proposed system, but in our system there are just 27. And then the total turn time is 7:21 for the traditional TS system, but for our system is 6:83. And the gate waiting time for all 4 trucks and the proposed system is lower. And the reduction in total turn time is dependent on the number of TS lengths and the ratio of truck to yard current. And this is the general bundle decomposition efficiency. This is your Groovy optimization. This is the Groovy. This is the general bundle composition runtime. This is their total turn time. And we can from this figure that the relative improvement ranges from 25.14% to 66.19%. And then we can get this conclusion. This study is the first to reduce truck turn time at marine containers by utilizing the concept of waiting area and TS to improve the scheduling of trucks once they arrive at the terminal. This study filled 2 research gaps. One is optimize the scheduling of trucks within each time window of the TS by using a new scheduling scheme that seeks to minimize truck turn time, considering both gate and yard operations. The second is develop an exact solution algorithm based on general bundles cut-based method. This is a reference. Thank you. That's all. Do you have any questions?
I'd say thank you, but it's a recording, of course. I think we've had a really nice mix of presentations here. I mean, we have connections on machine learning, connections between topics on freight, and then air quality on freight and passenger. Are there any final questions that anyone has for any of the speakers?
Thank you so much, Jason, for showing us the next set of sessions. You're welcome to stay here. Are you chairing this next session about Zephyr and travel demand modeling, or?
The next one is I am chairing a session, but that's in a different room. This one